Hello everyone, we're going to talk about safe reinforcement learning using control barrier functions. Here is the content that will be covered in this presentation. First, we have a short introduction about control of safety critical systems when the dynamics of the system is uncertain. Then two important tools that are used in the control design, which are reinforcement learning and control barrier functions, are covered. Then we go through the formulation of safe reinforcement learning, and then we will conclude this presentation. The diagram of a simple control system is depicted here. We have a system, we have some information about the dynamics, and by means of a controller, we want to bring the system to a desired point or tracking a desired trajectory or other similar objectives. But depending on the application, we might face further challenges. One of them are when the system is safety critical and we have safety constraints. And when we say safety constraints in a very simplest form are control and state constraint, it might be the limitation of the system itself, like the saturation of actuators or other constraints imposed by the environment. For example, here we have robots that are working nearby in a factory. They have a large workspace, but collision need to be avoided between them, so they cannot use the whole workspace. Here we know the trajectories of the robots, so we can design them such that they don't collide. However, we might have other objects or even human operators nearby, and we need to make sure that these safety constraints are satisfied. Another example is multi-robot systems. In this example, agents are told to swap position, but what happens is that they move to the center and collide, which is not something desirable. So we need to consider these constraints in our control design and make sure that all the safety constraints are satisfied. By the way, I will show the rest of this clip later in the talk to show how this problem is avoided. We have other challenges like designing an optimal controller, which is not always an easy problem to solve, and also this becomes more challenging when we have system uncertainty and or when our knowledge about the system is not accurate. These challenges are the main topics that will be covered in this presentation. And to address the optimality and system uncertainty, we're going to use reinforcement learning. Reinforcement learning in very simplistic form is just learning through the interaction. We have an agent or system which takes some action, and because of that action receives some cost or reward and tries to learn the best behavior based on this instant cost. And this agent tries to gradually improve its knowledge on what's the best way of acting, what's the best way of playing. One of popular examples of that are in the games. You see here that we have a player which takes some action, and because of that action receives some instant cost or reward, but there is a neural network behind it that is learning how to behave based on the instant reward that Mario is receiving. So like going up or going down in different situations, what's the best way of playing the game. Reinforcement learning in control is very similar. Still, it's learning through the interaction. And the goal is to finding an optimal controller which tries to minimize the long-term cost based on some instant cost. So we have a system, we apply some control policy, and we receive some instant cost. And we want to learn the optimal controller based on these instant actions and corresponding costs. Here I start with optimal regulation problem, and I'll go with discrete nonlinear system because it's a bit easier to follow the formulations, and then we'll continue for continuous systems. Here is the system dynamics that we have. We have a formulation for deriving the state of the system at time instant k plus 1 with some knowledge about the current time f x plus gxu. What we want is to find the optimal controller that stabilizes the system and minimizes a long-term cost function. If we, for a given value of input, if we apply some controller for this inner term, we call it value function. I will use this terminology again in this talk, and so please consider that when I say value function, it means just this summation term for some given value of uk. And if we write down as I said, we look for some recursive method, so we try to find the value function at the current time based on the value function in the future time. And one of the important principles that will come and helps us is Bellman optimality principle. And the idea behind it is that if we have some optimal value function at the current time, it means that all future time steps, it is still optimal because we had a long-term horizon which we have minimized. So we can extract this cost function at the current time plus the optimal value function at the next time. So it seems we are getting closer to a recursive formulation to find the optimal value function. This equation is also known as Hamiltonian-Jacobi-Bellman equation. I repeated this equation just for your reference here. And if we write down everything in one side, you see here we have the cost function plus the value function. By the way, it's not the optimal value function, it's just for some given value of UA. Minus v of x, it's called the Hamiltonian. It's the associated Hamiltonian with the input that we have applied. That it's not necessarily zero, but what we know is that if we have the optimal value function, this value would be zero because it's just bringing everything in this equation in one side. So we say, okay, we don't have the optimal controller, we form this equation and we try to successively get closer to h equal to 0. And it's one of the main ideas behind this method. And this Hamiltonian function, depending on how defined it, is either always positive or negative, and its optimum point is located at 0, which we can find by taking a partial derivative with respect to u. So if we have it, we can take the derivative with respect to u and find the input that minimizes the Hamiltonian, which is which gives us our optimum controller. But the thing is that we don't have access to V star here. So we need to find a method to approximate this value function. Okay, we said we try to find the optimum point of Hamiltonian at each sequence, and we need to try the optimal value function and the optimal controller. And we assign 2 neural networks to approximate these 2 functions. The network that approximates the optimal controller is called the actor network, which is our control policy. And the one that approximates the value function is called the critic network. So here we assign neural networks with some weight vector and basis function to approximate the value function and the optimal controller. And then using this available network, using this available approximation, we try to minimize this error, which also can be taken as the prediction error, which we try to minimize at each step. And here is the big picture we have talked about so far. We have a system dynamics and we apply some controller and we receive some instant cost. Using the instant cost that we are receiving, we try to approximate the value function and the long-term cost, which is called the critic network. And also using that, we try to find the optimal controller, which is the actor network. And how we are updating the network weights, our approach is that let's sequentially improve toward h equal to 0. But there is one challenge that we have not talked about, and that's we might have some safety and state constraints which we need to take care of. To do that, I'll go to the concept of control barrier functions, which will be used for ensuring safety. Here is a nice example from Georgia Tech, the research lab of Dr. Egerstedt. They have a remote access to arm robotic testbed, and people from around the world can use the MATLAB toolbox that they have provided. They can write their code and send it to them, and they will implement it in a robotic testbed. However, one of the challenges was that it was codes from research group. It might have problems, and therefore their robots were colliding. So they were looking for something to avoid this problem. And the idea that they used was based on the barrier function and trying to minimally change the controller that it was in their code or in their algorithms, and they just minimally change it to have a safe operation. I'll show you a clip from that, which I showed the beginning of it at the start of the presentation. Here, robots are asked to swap positions and they collide. Now, by means of a control barrier function, they go to the center, turn around, and go back to their desired position. And the controller was assumed to be not known ahead of time, so it was not possible to design a specific trajectory to have a collision-free behavior. This worked with a larger number of robots. The only thing that they're doing is that they are trying to respect a barrier function condition as well. And that enforces a safe behavior. Even one of the agents are just going toward the rest of them, still it works fine. Okay. So I'll go and explain what this barrier function is and what it is doing. Before doing that, when we want to have safety, we define the safes that we need to formalize what we have. Here we have a system dynamics, and we define the set of safe states. And I'll give an example of what this safe set is and how we can define it. As one example, consider the adaptive cruise control problem, or original control objective is that our ego car drives in a desired speed. However, if we have some front car ahead of us, we need to make sure that no collision happens and the ego car slows down to adapt to the flow of traffic. So we have some relative distance with the front car, and we have some safe distance. So our safety specification is that delta x minus d equal or bigger than 0. Now using the same safety criteria, we can define the safe set, which are the states such that the safety specification is satisfied. Now, what we want is that we want to stay within this safe set because our states are safe within this set. So we use the concept of forward invariance of a set. Assume we have like a state space which is all possibilities, and we have a safe set which is just a subset of this set. So the idea of forward invariance is that if we have a state, we have some initial condition within the set, we want to make sure that the state of the system will stay in the set for the long time. So if we are here in this set at the current time, we would remain in this set for always. And the question is, do we have a tool to make sure that the set is forward invariant? And the answer is yes. We can do that by means of control barrier functions. They're conceptually similar to Lyapunov functions. To make it closer to mind, I bring the example of Lyapunov function as well. Assume like we have a positive function which is decreasing, then it enforces the trajectory of the system to move toward the origin because it cannot pass any of the level sets. So it's used for stability of the system, and the level sets are always shrinking. Control barrier functions are less restrictive. The level sets do not need to always be shrinking. Just we want that one level set, which is defined by our safety criteria, never be passed. So assume that we have a function h, which is positive in the set, and becomes 0 at the boundary. Now, if we have a positive derivative at the boundary, if the trajectory, I give example from the adaptive cruise control problem, h was the distance that we had. If this distance decreases, it's like the car are, getting closer to each other. We are getting closer to h equal to 0, which is dangerous for us. Now the derivative becomes positive. When we have a positive derivative, h has to increase. Okay, so when h increases, it means we are the trajectory is pushed back inside the set. So the safety of the system is satisfied, and this set remains forward invariant. We went through the concept. Now the question is how we can actually employ this barrier function. Well, the first thing is that we look for a barrier function candidate, which is positive in the set and goes to 0 at the boundary. And if you look to the definition of the safe set, the function for defining the safety criteria itself is a barrier function candidate for us because it's positive at the boundary and at the safety, it's positive in the set and is 0 at the boundary. So finding a zeroing, there are two types. This one is zeroing barrier function. So finding a zeroing barrier function candidate is very easy. But it's not enough. We need to make sure that the derivative condition at the boundary is satisfied as well. So we write the derivative of h, which is the partial derivative with respect to s, and the derivative of x with respect to t. And here is when the system dynamics appear here. Now to have h dot positive at the boundary, we form this criterion. So this part is just h dot, and we added alpha h as well. Alpha is some positive value, and h is the value of safety criterion that we had. The reason we added this one, if we didn't add alpha h here, then h dot had to be positive all the time, which was restrictive to us. We didn't need that h dot be always increasing. It might increase sometime and decrease sometime, but just at the boundary should be increasing. So here, if h gets close to 0, then this derivative becomes positive. And therefore, this h dot positive at the boundary will be satisfied. And as you see here, u appears here. So here is the point that it gives us the control, it gives us the power to make sure that this constraint is satisfied, because we can control u and we can design it such that this criterion is satisfied. Then by designing a proper control input, we can make sure that our safe set is forward invariant. And one of the common methods to integrate the barrier functions into a controller is using a quadratic programming. If you see this formulation, it's linear with respect to u, so we can have a solvable, easily solvable optimization, and we have some control input. It can come from LQR or any other method, and we try to find the closest input to that controller such that the safety of the system is satisfied as well. And this is the method that was used in the Roboterium example that I showed you earlier. But still there's one challenge with this method, and that's we need information about the system dynamics here. So we need to have full knowledge about F and G to design a safe controller, and this is the thing that we want to avoid. There is also another type of control barrier function, which is called reciprocal control barrier function. It's similar to the previous one, with the difference that we have, at the boundary, our function goes to infinity. One simple example of this function is 1 over h. H is our safety criterion, so which is 0 at the safety boundary. So at the safety boundary, b goes to infinity. Now we need another derivative condition, b dot negative. Okay, so if b increases and tries to become very big, b dot becomes negative, and then it will get away from the boundary of the safe set. Okay, now we want to take the advantage of the both of methods. Reinforcement learning provides us a method to design optimal controllers for the systems that their dynamic is unknown to us, but we have not safety and constraint specifications. On the other side, we have a strong tool in safety specification, which are control barrier functions. However, they are model-based. So we want to take the advantage of both and design a method which gives us a safety optimality, and when we have an uncertain and unknown system. Previously, we had this optimality formulation, but we didn't include the safety. To have the safety included, we need to have another constraint here, which is, the state of the system should be within a safe set. Okay. However, even without this one, it was a hard problem to solve. So instead of having this constraint, we incorporated a barrier function into the cost function, and we changed this one just to initial condition. Later, I'll explain how it is working, and there are some conditions that the barrier function should have. Again, being positive inside the set, going to infinity at the boundary, and also wanted to be monotonically decreasing, so it kind of gives us an index how much we are close to the safety boundary. And here is a logarithmic function we use as a barrier function candidate. The thing that happens is that if we get close to the safety boundary, which is the worst case that we can still tolerate, b goes to infinity. Therefore, this term becomes dominant, and the optimization will act in its descent direction, so it never let b goes to infinity. That's the idea behind it. And the reason we are using a logarithmic function is that it rapidly damps as it gets away from the safety boundary. So it's actually play a role when we are getting into an unsafe condition. And also with this parameter gamma, we can trade off between safety and performance. And by performance, I mean, the original controller that we had, we wanted to minimize this long-term cost function. And, in this formulation, we just don't say, let's avoid, the risk. We are also planning for that. So it's an optimized safety. But the thing is that we want to have safety in a model-free successive approximation. In a reinforcement learning framework, we wanted to gradually learn the optimal controller. How? Now, the question is that if we are gradually improving our knowledge about the controller, can safety still be satisfied or not? The answer is fortunately yes. I don't go through the mathematical formulations. You can find them in the paper if you're interested to know about that. I just give a sketch of the proof that we say, assuming we have some value function, if we just go through that successive approximation, what happens with our barrier function, and it will be shown that barrier function remains bounded at each iteration. And using that, we say, therefore, we can have safety in successive approximation. Okay, so far safety is ensured, but although the safety should be always prioritized, we also were concerned about the performance as well. We had some original control objectives with which we want to make sure we get into it if the safety is ensured. Like in adaptive cruise control problem, if there is no front car, there is no heavy traffic, we want that the car drives in a desired speed. Here we can show that the stability of the system is guaranteed because, in RL framework, typically that value function is taken as a Lyapunov function, and it will be shown that it is shown that it remains bounded. Therefore, the system don't become unstable. But it was kind of the minimum requirement. We were interested to have optimality. And one of the challenges when you add something into the cost function is that you're actually changing your optimum point, because previously we had a function based on x and u, and when x and u were 0, that point was 0, and we had a specific optimum point. We have now added something into it which changes our optimal point. So the question is that can we still get an optimal performance or not? To investigate that, we defined a safety region, which we can check the optimality when safety and optimality are not in conflict. When they're in conflict, safety should be ensured. But when they are not in conflict, we want to get a good performance as well. So we define a safety region, which is the safe set consisting the origin. What this means is that there is a safe trajectory within our desired set such that we can reach to the origin safely. And then we investigated the behavior of the system within the safe region. To give an example, consider that V is our value function, which its optimum point is located at 0. And here two barrier functions are plotted. One of them is for gamma equal to 1, this red line, and one for gamma equal to 10, which is the yellow one. And as you see, both of them goes to infinity at point minus 1.5. For the value of gamma 1, you see that we have some deviation from optimum point, but for the value of gamma, this is almost equal to 0. So the idea is that if it depends on how much we want to get close to our original optimum point, and with proper selection of gamma, we can get arbitrarily close to origin. And the result is that yes, we can have a good performance if it's safely possible. Okay, here is the big picture of the work we have done. We said we need safety in our reinforcement learning framework. So we first reformulated our problem by augmenting our cost function with a barrier function. Then we checked whether in a, gradual improvement of the controller and in a successive approximation, can we have safety or not? And then we said, okay, how about the stability and optimality? And we find out with proper selection of gamma, we can have a good performance as well. And the last step is implementation. So far, we have just said, assuming we have some value function, but the question is that where this value function is coming from. They're actually the networks that we are trying to train, so it comes to the implementing algorithm. And we have used off-policy reinforcement learning algorithm. In an off-policy algorithm, we divide the control input to two different inputs. One of them is the behavior policy, which we apply to the system to collect the data. And the other one is the target policy, which we update toward the optimal policy using the collected data and without even applying it to the system at the, at the iteration phase. And to find the policy-Bellman equation, this equation is just very similar to the one that we had for the discrete case. We just have it, in the previous one, we had it for two different time instants, and just we extracted the cost function at the current time. Now here, since we have a continuous form, we have integral over a short period of time. And this controller is just, the minimizer of Hamiltonian, which can be easily found. And if we integrate these two with the new formulation, with new formulation of dynamics, it gives us the off-policy Bellman equation, which is the main equation that we iterate on. So we now need to assign neural networks to approximate the value of the control policy and the optimal value function as well. And we can apply the controller, collect the data, and solve it using least square method. And just one point that I want to add is that if I don't know if you have worked with reinforcement learning or not, but one big phase of implementation is actually training your networks, because there's a condition, persistence of excitation condition, that needs to be satisfied. In other words, you need to excite the system in order to be able to properly train the network. And using this off-policy reinforcement learning, it's much easier to train the network, and it's much easier to make sure that PE condition is satisfied. And here we have simulation results for a lane changing problem. The problem was to change the lane, which was the lateral displacement. We want to get to a desired displacement, but we want that a critical value won't be passed. So we augment the cost function with our barrier function candidate. We assign a basis function to learn the critic and actor networks. And then using the method that I mentioned, we train them. And here are the simulation results. The weights of actor and critic are converge, and here is the states of the system. Here we have applied the noisy input and collected the data. Then the learning is completed and the controller is updated. This red line is the critical value that we want not to be passed. So without the barrier function, if we apply the just the plain reinforcement learning, this line will be passed, which is by contract to considered an unsafe state. But with incorporation of barrier function, it gets closed to desired point as much as possible, but it has not passed the safety boundary. And other states have also converged to zero. As a conclusion, we went through the importance of uncertain safety critical system. We went through reinforcement learning, which is learning through the interaction framework, and we approximated the long-term cost and optimal controller by means of critical and actor networks. Then we went through the control barrier functions, which are used to ensure forward invariance of a specific set, and we tried to make sure that our safe set is invariant. And then finally, we integrated these two methods in a safe policy framework. We augmented the cost function with barrier function. And then we investigated the safety, stability, and optimality of the system. And finally, it was implemented using an off-policy algorithm. If you are interested to know more about the details of safe reinforcement learning, you can find it in this paper. Here are good survey tutorial papers on reinforcement learning if you're interested to know more about that. And also these are good papers on control barrier functions and also the references within the clip I showed you earlier. I want to thank my PhD advisor, Dr. Kim Marcy. This work was under her advice in Autonomous and Distributed Control Lab with Michigan State University. I also would like to thank Dr. Taghirat for having me here and also for everything that I learned through my membership in ARAS. It was an inspiring and great period of my my life. Thank you so much for that. Okay, thank you so much for your attention. I'll take any question.
Thank you very much, Lara. It was a very good lecture. As expected, step by step, we learned a lot how you develop the idea and how to integrate things together. I have a few questions, but before it is better to have the question of the audience. But before starting, there are some problem with the names of some of our audience. I appreciate if you can just check your name and you can just click on the name and just rename your name to your actual name, because we have a number of guests without their actual name here. You can check the list of audience, just open your microphone, you can see which one you are and you can change your name. If there is any question, also Reza told me that there are some, it's possible at the end that we can have some chat with Dr. Reza Abchelu. If there is any question, please just raise your hand and unmute to ask your question. There is a question in the chat box. Maybe I can read that. There is a question from Habib. Thank you for your presentation. It was great. This is my question. Can we use RL for fault detection? If yes, what is benefit of using RL for that? And is that implement with regular RL method, or we have to do something hybrid or anything else? Zahra, do you have any comment on that?
Like you mean actuator fault or something like that?
Yes, it could be actuator, it could be sensor, it could be something malfunctioning in the system, the fault diagnosis and the fault tolerance system. The main question is somehow different from your work, but do you have any experience of using reinforcement learning in the fault tolerance system?
Not actually. Typically, they detect the fault and try to isolate it. And since reinforcement learning is, tries to do the interaction, I don't know if it's, I don't really understand how, we can do that with the fault. No, unfortunately, I'm not familiar with that.
Let me ask two questions. Maybe the other audience can also please either write your question or just raise your hand to have your unmuted and having it. If you can go to your slide number 20, Zahra, if it is possible for you to go back. I have a main interest and some concern here. Yes, maybe, yeah, this is good, or even one slide before that. When we are talking about positive invariance, yeah, that was, yeah, exactly this one. My main interest is, your comparison of control barrier function to Lyapunov level set, and you know that how eager I am about this Lyapunov level set, and especially V is equal to 0 and the benefit that we can get on that Lyapunov level set. The issue that we have, you go to the next slide. The issue that we have is the boundary that should be is equal to 0, and also the invariance set that we make sure that inside the set everything is going to be fine, and then having the derivative condition there. You mentioned that it is not very difficult to do that if you have the level set, if you have the barrier function defined as an inequality constraint. I just want to have some more comments on different aspects. If we have different applications, if we have some sort of some physical properties as barrier function, which are not very easily can be written in a inequality, some simple inequality condition. What will happen there, and how we can find some invariant set on that condition?
Okay, that's a very good question. Actually, this well, it's typically a general method, but it cannot cover all possible safe sets. But here, it's just not necessarily one single function, so it can be matrix of different functions. So one thing that comes to my mind is that even a general set, we can use partitioning to at least cover an over approximation of our safe set. We partition it and we define it using inequality constraint. So I think some over approximation of that safe set can be expressed by inequality constraint, at least for a class of safes, for a class of sets.
Is it somehow related to LMI's linear matrix inequality? Can we have embed that portion of the theoretical representation of an inequality into some linear matrix inequality, bringing it into this picture, or is it done already at that side?
I have seen that the matrix of H is used for defining the safety. Yes and no, I would say.
You know that there is a rich literature on
yes.
linear matrix inequality and how we can develop that, and depending different a control problem can be be recapsulated or reformulated into that function.
Yeah, actually that's a great idea. I have seen some basic things on that, but I think there is much more to be done there.
Very good. My second question is mostly on the RL part. I don't remember the slide number, but if you can go further ahead and then just actor critic criteria, and then my question is, the Hamiltonian recursive, just go a few more slides ahead. The Bellman equation, go ahead again, optimal regulation problem. This might be the general idea of reinforcement learning. What we have in this issue that we have thought about it, when we having some learning in the loop, when we are working in the loop, when we are learning, the stability is one concern, but there is another concern about convergence of this learning math or the adaptation that we are doing. Can you speak about that? What is the difference? Is it really related to the stability of the closed loop system, or these are two different distinguished problems? And if there are, I think there are some special issues on convergence. Can we have somehow this convergence to be guaranteed or to be applied to the real traditional and uncertain system?
Okay. So the question is if one was on stability of the system and the other one if we can guarantee the convergence, right?
Mm-hmm.
So one thing is that they, in the very initial proofs of RL, they typically employ the value function as their Lyapunov function. And the thing is that if we have a sequence inequality order of Hamiltonians that we are, approximating, it gives us, the same sequence in our value function, which I mean, like they say, h is decreasing, therefore we have a decreasing value function as well. So it's it's a bounded function that they're taken as Lyapunov function, and they show that the stability of the system is preserved. But the thing is that h equal to 0 gives us the optimum point. So the question is that if it's the local optimum or the global optimum. So I say it needs some assumption to make sure that it will converge. It will converge to the optimum point, but I think there's no guarantee to have it's the global optimum.
Okay. So there is no guarantee, or there are some guarantee. I just want to know if there are rigorous proof about the convergence or not.
There are some guarantees, but they have some assumptions for that as well. So it's not a generalized.
That's not rigorous. Okay, we have a few questions here. If you don't mind, I go one by one. Amir P. Waladbegi has asked that, could you please tell us why you have used such log function as barrier function? The log function as barrier function, what is the benefit of that?
Okay, that's a very good question. Let me go forward. It actually comes to play when we are checking the performance of the system. So you can use any function that satisfies the three conditions, but something that helps us with use of logarithmic function is in the performance, because we are adding our value function with some another function, okay? And that function might change our optimum point, which is not desired to us. We like to reach to this point, okay? So it's important that we have a function that can rapidly damps as it gets away from the safety boundary. Here the function goes to infinity at our safety boundary. Here we take this point as our safety boundary. It goes to infinity, but it rapidly damps. So we can adjust it such that it becomes kind of, negligible in the rest of the area. So it just comes to play at the safety boundary. Here is the reason that we use the logarithmic function. And what was the other question?
No, it is the same thing. He has also another question. Have you used any exploration noise in your method?
Yes. Here we have two different policies. One of them is the behavior policy, and the other one is the target policy. Behavior policy applies some noisy input to the system, which needs to excite the system, but then we use that collected data to update the target policy. And target policy just updates toward optimum point without, any, by means of the collected data. But yes, in behavior policy, we need to add noise to excite the system.
Okay, very good.
I guess
still, yes, go ahead.
I guess there was another question. As you know, the proof of stability is really challenging during the learning process.
Yes.
Could you please describe how you did this proof? Okay. Yes, during the learning, we need to have some partial knowledge during the learning, during applying the behavior policy. The system shouldn't become unstable during that, but it's, a common assumption in reinforcement learning framework.
Okay, I see again that a number of audience have the name of Muhammad Qaderzadeh. I think they've used the link that Muhammad has provided to the people. So we have about 5 people with the same name of Muhammad, and I think Muhammad is gaining quite popularity in this talk. One of them wanted to ask a question. They can unmute and ask your question. I don't know, but please introduce yourself if the person who has put some question in the chat box.
Hello, can you hear my voice?
Yes, please introduce yourself.
I'm Ashkan Seferi, actually bachelor student of electrical engineering, Faculty of Electrical and Computer Engineering, University of Tabriz. I'm so grateful for actually participating in this great webinar, and thank you very much for your such an informative presentation. I wanted to know, as you are experienced in applying for USA actually universities, I wanted to know a roadmap of applying for these kind of rank and top universities. Actually, I'm a top student of my faculty, and as well as the fact that I'm the actually bachelor term 4 student, but I have published multiple ISI papers, book chapters in Springer in actually publications, and even the national books in my own country. I wanted to know a roadmap to applying for these kind of rank and top universities, and I assumed MIT University for my PhD and postdoctoral course. And as your experience in this process, I wanted to know a roadmap. Thank you very much.
Of course, this question is somehow quite different from your presentation. But if I just make it a bit, how is your experience about gaining experience in Iranian universities and using them in very top universities in the United States? What would be your main recommendation to the students who are really doing a great job in Iran?
Okay. Well, it's good that you have a good resume and you have like good English TOEFL scores and things like that. And the other thing is that here there are some maybe openings that they rapidly fills, and sometimes there are funding issues. So I would say it's really important to be active and get in touch with the different faculty, different professors that you like their work. And it's important that you find some opportunities there. It's a little bit chance included in that. So I would say, first find candidate a couple of universities and a couple of research labs that you are interested in, and then get in touch with the professors. Feel free to do any part of research if they recommend you to do anything, and then apply for the universities that you want. And I would say if there is a professor that it's willing to work with you, it's the chance of admission will increase.
Okay, very good. There is also an exact answer from Professor Reza Babchelu, one of other former ARAS alumni, said that I have a usually open position. You may send your CV to me. So usually it is important to get in contact, get in touch with distinguished professor around the world. And such webinars and such technical talks could help people to get to know each other. Thank you, Reza, for your great offer, not just for Ashkan, for other students who are willing to have a roadmap for their studies abroad. I suggest you to work very hard at your home university and have a great experience as much as you can, and then use your resume to follow up the thing. There is another question regarding your talk. Can we use this BLF for output constraints? I mean, if we have y is equal to cx, a combination of states, can we also include that constraint in the BLF?
Yes, if you can represent it as some inequality constraint, it's a general form. It just needs to be a smooth function. It can be function or combination of states. Yes, you can do that.
Perfect. All right. It seems that I read all the question in the chat box. If there is any other comments or question to be added at the end of the talk, we are almost 1 hour now. We are almost getting the edge of the time that we have. Reza Tahiri asked that noisy state measurement, will this work? And then we have also Reza for his comments. Noisy state measurement. If you have measurement noise, what will happen? Is it usually naturally in the system? Does it provide any problem, cause any problem?
Is it for the general, for RL, or specifically for this work?
For your case, I think for the barrier function.
Actually, that's a good question. We have not, considered the measurement noise. We assume that, we apply controller and we, can get some instant cost.
And also on all your states, we might not have all the state available. This might be the open horizon that you can, have some sort of some estimation of the states as well, and some measurement noise, output feedback, some sort of output feedback.
Yeah, that's a good question, because we are learning based on, the instant cost that we are receiving now. The noise might alter that instant cost. Yeah, I have not worked on effect of that for estimation.
Okay, thank you very much, Lara. It was a very great pleasure having you with us.
Thank you very much for having me.
Okay, I would like to ask both Reza, Dr. Ghabchelu, if it is possible to open the camcorder and please talk. And also, if Mahdi is available still with us, I would like to ask himself to open his camcorder as well. It's a long time. 3 of us are not together. It happened like maybe 2 years ago, but I think it goes back to more than 22 years ago that we were in the same lab working. Thank you, Reza. Please go ahead, and we have your...
do you hear me?
Yes, of course.
Yes, good. Because I'm using my Bluetooth mic. I'm not sure that... Okay. Thanks a lot for organizing this webinar. And yes, that's true. Me and Mehdi, we've been... probably we were the first master's students of Dr. Tahiri. Been always nice to follow some of the works you have been doing after that also. Unfortunately, I've lost the contact mostly, except a few true researchers, but not really doing research. First I moved to Portugal and then now in Finland. But I always enjoyed and I always remember what we did, and been always proud of the group you have there. So thanks a lot. I have a couple of comments and questions, but I will, if there's a time. But I'd like to also hear Mehdi's voice. Been a few years. The last time we met in a conference was Accra or somewhere.
Yes. Yeah, it was probably Accra in Sweden.
Yes.
Stockholm. Yeah, it was. I think 1997. You returned from McGill, Dr. Tahiri, right? I think that was. And then Reza and I were the first master's students with Dr. Aprishamchian. Co-supervised both of us with you and Dr. Aprishamchian. So it was a great time. Hopefully we can catch up again in a conference somewhere, maybe in Iran. And
well, it's been virtual, so there's more chance to meet apparently than actually physically. So
Yeah.
When I come to Iran, I rarely go to Tehran. I directly go back my home. So I've been avoiding Tehran mostly, but maybe I should come to Tehran as well to at least to meet the old friends.
Yeah, actually, we have a ICROM conference, International Conference on Robotic and Mechatronics. We had the pleasure of having Mahdi as one of the keynote speaker, I guess 2 years ago or 3 years ago, I don't remember, a few years ago. And it is a very good open forum for joining different people in the field of robotic. This year, we have organized that conference quite all virtually, and it is very interesting I will share something with you that we have already 4 very, very top keynote speakers who honored us to give a speech. If you have time, I appreciate if both of you and also just the other people in this room, I see a few professors from Iran. The names are familiar with me. I just welcome Dr. Huda Moody, one of the assistant professors in Iranian University, and other people who are helping us in organizing that conference. We appreciate if you can contribute in any means, if you can provide us with...
I actually received the invite for the
you have
conference.
seen that.
I've been thinking what could be the topic.
Yeah.
Haven't with the topic yet, but there's a good chance that we will submit something. Actually, one of my PhD students.
Yeah,
also
if you submit a paper,
yes.
or maybe something together, we can, or a workshop. That would be also great. We have more time to, to have a even joint workshop. I don't know if it is possible or not, but it is.
Yeah, we are working in RL. Definitely, we are working on imitation learning. We are working on safety. Actually, my PhD student who is working on RL is now online listening today. But the machines, of course, we are doing. We are mostly working on real practical stuff. Like you saw these machines we have behind it's like tractors and excavators and loaders and these kind of machines, heavy stuff. Those are the robots we move. Special because around region we are very strong international companies around here, so we are funded mostly with these companies. Very little with health and
that's more fun. Like what you do. I see your pictures on LinkedIn. Driving one of these tractors.
Yeah, very large tractors.
Yeah, that's the smallest one we have actually. That's about only 2 tons. I have a 20-ton excavator in the lab.
20 tons. That's perfect.
Yeah. Reza always picks the fun stuff. So previously he was working on underwater robotics, always on the beach, and
when people talk about Zahra talking about, but people talk about safety and RL, I laugh really. They don't really understand what is safety. You just need to walk next to this machine and see the sound. It scares you up. Yeah.
Very good comment.
We are running RL on this machine, so we have been working. Actually, Reza, it's my PhD is also Reza's name. Mm-hmm. Running RL on those machines. So safety is one big thing. Regarding that, I can have one question. Maybe there was a very interesting question about the output safety, like not only state set for the state, but for output. Of course, theoretically, you say it's just function, but in practice, it's usually easier to define the output safety. Let's say you want to say manipulator that doesn't hit the ground. Okay, your table. That's easy because you say, okay, the whole point of RL is that you say, I don't really know about the system. But then is a contradiction saying that I actually know the safe state. How do you know that? It's impossible. I mean, in practice, it's impossible. Now, of course, you always know something about it. It says, what are those? Well, of course, you can set a lot of theoretical interesting problem, but in practice, outputs are typically more easier, intuitive to define. Like the car example you said, is that the states is not actually state, it's actually output, because the distance is the output. Your states are velocities, accelerations, all positions. So it's not about you practically define for output stability and safety. So so how you define it, how you learn it even? Can you learn it? That's also one question. Can you learn the safety set? I think those are interesting problems. We haven't looked at it, but whenever we talk, I also always pose this. When you work with the real machine, you see that there are some real problem that nobody even think about it. It's because you assume it's given, it's a theoretical mathematical problem, but in practice is different.
Yeah, that's a very good point, actually. For example, we don't have the information about the system, and that's why we need to have some learning frameworks. But for safety, like if there is collision avoidance or things like that, we know the general formulation. So, for example, we want to have a safe distance, so we know that this distance should be bigger than some value, or it can be more complicated constraints. But then when we include it in our cost function, we're not actually having it, we're learning it. I don't know if it answers.
Yeah, but, yes, I know. For example, think about the manipulator. You can say, I don't want this to hit the ground. Okay, you can define as abstract for it. You don't want it to reach to the limits of the hard limits of the joints, right? But then it actually need to have numbers there, right? So how you do that basically is that when to have the numbers means that you need to know exactly the sensors. You need to. I lost my microphone.
Could you give an example that we don't know what the safety is?
Let's say, well, the manipulator. Think about the 2 degree of manipulator. You have a sensor installed, okay? You don't know where the sensor is. Means that if you connect it and measure the sensor, the encoder, if Reza installs it, the encoder installs it this way. If Mehdi installs it, he might install it that way. So when you measure it, the same manipulator position gives you 10 degrees, the other one will give you 20 degrees. How do you define where is the safety limit or the joint limit? So either somebody has to calibrate it beforehand. It gives you a nice industrial manipulator, calibrate it nicely. Then, of course, I agree with you. But if it's a system that you don't know about it, it's impossible to tell.
Yeah, if it assumes an accurate measurement, yes.
Exactly. You assume it's installed, calibrated nicely, and then you know the sensor camera is measured and it's placed here. You know many things about it.
But I would like to add a comment on that. Although we assume that we are measuring properly, the thing is that we are defining safety as in the optimization. We are actually planning for safety. So we can say say, okay, we don't have exact knowledge about the system, or measurement might not be accurate. So let's consider more margin for the safety. So we can put more emphasis on the safety and make sure that with a higher margin, it doesn't reach that extreme point. And if we have better knowledge about the system, if we are more certain about measurements, we can design it such that it just only comes to play at the safety boundary.
Okay. But then one more question. Well, these level sets are the key thing here. They have been around. They are the center for proofs in Lyapunov, right? This is the same thing. The only thing is just they call it nice name. They have a nice name for it. Safety certificates. They have been used also. The same techniques and tricks have been used in Lyapunov state constraints beforehand. I have a historical question. Why this is barrier function name? Because barrier functions have been around for optimization, have been used to kind of make sure that some of your states during the optimization doesn't exceed certain bounds. They have been level sets and similar techniques have been used with Lyapunov, together with Lyapunov, to guarantee some of the states don't exceed safety sets. But why barrier functions have become like a barrier certificate have become like very popular all of a sudden in the last few years? Do you know? Just a historical question. I don't know, because I have used it. I don't know, when I did my PhD. I have papers on it. Yeah. But not the same name, but just different.
Yeah. I don't know the history of it, but one thing that I would say is that like the other methods that we have for safety, like for finding the reachable set or things like that, it's less computationally expensive, and also the constraint is linear with respect to your control input, so it can be easily integrated to the controller that we have. And I see in many papers they're using this optimization method. So I would say maybe, the ease of integrating it to the existing controller might be one of the reasons that it's becoming very popular.
Okay. I don't know if Dr. Tagir or Mehdi knows about them.
I have a comment on you, Reza, on your attitude. Not changing after 23 years.
Are the same?
The same.
That's good. No, I think that's good then.
Still very, 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 very attractive, especially, the way you're attacking the students in the defense. Do you remember that the old time that we have, the defense in our department, especially when we have defense in neural network and that area, it was like this thing. I don't know if you remember that time, but the same thing, just asking some question, bringing everything down. Just historic. Of course, Zahra is a user of this theory,
sure.
Not the developer of that, but very good. If you can also just give us your, experience, since you said that you're using RL, and actually we have also started using RL in our surgical robotic application. We call it, as you mentioned, another way, but we saw that the barrier function can become to the picture. But as you know, I have always been reluctant in implementing something which is still under development in real industrial plants, especially when there are the safety and stability is of course main concern. Just give us how much attention or how much confidence you have on using this kind of intelligent or reinforcement learning or some learning in the loop approaches in practical application.
I think there are kind of the main reason that I see it. Of course, we have been working on that for very recently also, so my knowledge is limited. But this is the way I see it: is that things are more or less the same thing we have been doing. There's a system identification, there's an optimal control, all are there. The difference is that you have now better tools to fit a model. We just used ARMAX or something to fit a linear model with some or gray box with parameter optimization, etc. We found model, we fit the model. Expert operators sit and see the system, make sure that you fit something that actually fits, and then you know that what's the limit of frequency and bandwidth of the system, until what frequency you need to identify the system, etc. You do all these things, and now everybody forgets those and say, let's send thousands of different control trajectory, and then and we have now powerful neural networks and very expressive and fit a model and or just learn the policies. Okay, there are very powerful systems that learn. There are powerful optimization toolboxes. I think that's the main reason. Of course, there are ideas are just developing and emerging from different routes coming together. There are computational. You can run these things in real time. I was telling my Reza that you can even control a system just by by learning the DC gain of the system. You just need to limit the bandwidth. You have a PD control, it will work. Now, depends what you want to do with the system. How big network you want to fit to it. Well, it doesn't really need, these things, I guess the main things have been forgotten. Let's say we have been, of course, frequency domain design have been around because of the graphical design, human-friendly design, etc. Then time domain design came, and now we have all this, again, it's still we are in the time domain design. I guess the thing that we are forgetting is that there are a lot of knowledge out there that can be exploited. We should learn the basics.
Okay. And still we have still the problem of getting trained, you know, this trainability, and also the large network that you have has its own problem in getting the training process always still over there, which that's usually not well given in the papers, but this is a problem in the background that you mentioned. And also something like the measurement, the noise, the practical issues that should be.
For example, Zahra's method is deterministic. When you go to stochastic, then it's a chance constraint problems. You have techniques there from stochastic and probabilities. And it may be a bit different settings, but of course, many of these things are kind of extend to those. But that's why I'm very interested in practical stuff. When you come actually implement a real system, you see that you need a lot of knowledge before actually can even implement something. No? Safety is the first. Safety is the first. No, even defining a safety set is the first before everything. And as I'm saying, in practice, you can't really easily define it. At least I haven't found the easy way of doing it. I have some idea. You can do it with maybe imitation learning. That could be one solution to it, but I'm not sure.
All right. Perfect. Thank you, Reza, for sharing with us your.
Sorry, I haven't changed.
No, it is, you have, of course, you have changed. You know, if you look at your hairs, you know.
That's it. That's true.
You have been lots more experienced and very well. Thank you for joining our webinars, and I hope that we have this friendly chat at least every month or every 6 weeks, that we have this open discussion. And if you find it also suitable, you can be one of the speaker in the next, month, if you have the time. Of course, I don't want to push any pressure on you, though, but we have the opportunity to bring everything from all around the world to have some benefit to the Iranian community, especially in the field of robotics and control. So your precious experience will help us to do that. And I hope that shortly we can meet, even you are coming in Iran and going just straight to Urumiyeh, just let me know. I can be your guest for a few days.
Thank you.
And the same thing with Mahdi. If Mahdi is coming and going directly to Mashhad, it is all Iran. We can be together.
My wife, is from Karachi. I have to come to Tehran all the time. I spend more time there.
Very good.
Just an advertisement. I just post something. I have a lecture or workshop in a numerical optimal control. I think it's a week or two. The only problem with this timing for me is that my kid comes from daycare, and that's why it was a bit noisy here. I sent her out. Now she's a neighbor. That's why I'm.
No, it is fine. We are fine with the kids' noise. No, don't worry. Especially after 1.5 years of having electronic classes, e-learning, everything will happen in this session. So we have quite been experienced in that. Okay, thank you very much, everybody, for being with us. If there is any comment, Mahdi, if you have anything to add or something, if you have some experience in RL or something, just please.
No, I agree with what Reza said, and I think for health, one of the issues is that we don't have much data, really, and we don't have much time to let an algorithm learn on a patient's body at all. So, so as far as control design is concerned, I don't think I don't see too many open problems in terms of control that requires reinforcement learning. But there are opportunities for using networks for skills assessment, for instance, and kind of data-driven methods that are not necessarily control problems, but still they are problems that have to be dealt with. So I think the way forward for medical robotics is kind of a combination of a model, maybe an inaccurate approximate model, plus some sort of learning. So you have a baseline model, and then as you grab data, then you have an element that adjusts the model. Sort of like adaptive control, but without having the dynamics, without having a dynamical law, but with data-driven methods kind of augmenting it. So I think that's just my take.
Okay, thank you very much. Zahra, if you have any concluding remarks, please go ahead.
No, Jeffrey, thank you so much, and everyone who attended this conference.
Thank you.
Thank you very much. Thank you. If we could have maybe a get-together picture all together, if there are some people who have their camcorder and they can open it, please just come up and take on your camcorder. And I would like to ask also maybe Mohammed or Mohammed Jabbar, the people who are helping us. Actually, I am right now, Reza, I opened the link that you have sent to us. It seems to be quite interesting. It will be in June 18th. It's not much ahead of time, about 2 weeks, I guess, or 3 weeks. So I encourage all the people who are interested to also join this workshop quite well. Okay, just let me open my screenshot.
By the way, today ICRA has started, and
yes.
The workshops are just running now. Actually, they are
right
free.
Now.
Yeah, and also on June 4th, Friday, I have a workshop there. But also all keynotes and plenaries are free to attend.
Free. Yes, I encourage all the students, all the people here, to take advantage of this opportunity. Participating in ICRA and ARAS it was very, very difficult in terms of expensive time that you should spend, especially today that the workshop in the ICRA is much of interest that people can basically attend. So I would like to take a picture. Just please, everybody, smile if you have the camcorder. We are still looking for some new camcorders getting on. Just 1, 2, and 3. No, it was not very good. If you remember, if you don't mind, I just take another picture. 1, 2, and 3. Okay, I will share this picture with all of you, and wish you all the best, and welcome you to join us and follow us in the next webinar. Thank you, Zahra, for your very excellent talk, and I wish you to graduate soon and get back to Iran and help us with so many problems that we have in
Sure,
thank you very
so
much, everybody, and take care of yourself. Bye.
Bye.
مواظب خودتون باشید. خداحافظ.
متشکرم رضا، خیلی عالی بود، دست در نکنه. مهدی جان تشکر. خدا
در تماس هستید. خدا.